It's good to see you. Thanks for a great turnout. In terms of domestics, any fire alarms, we're going to follow each other and just get out as quickly as we can. Apparently there's no scheduled fire tests or any other expected emergencies. I'm just going to open up. I'm Geoff Prudence, I'm Chair of CIBSE Facilities Management. Tonight is a joint event with the CIBSE Facilities Management Group and the CHP Group. Phil's here who's going to be speaking, chairs that group. I think it's right to say, Phil, we're probably one of the most active two groups amongst CIBSE's sort of interest areas. So we talked about doing this, so really great opportunity to bring everybody together. But particularly thanks for Ener-G for working with us on not only speaking and putting this event together with us at a fantastic venue, but also sponsoring the supported evening for drinks and refreshments that some of you have seen already. Thanks for everybody giving up the time to come, and particularly the speakers. FMs, designers, operators, whatever across the spectrum. There's a cross-section of people here tonight who will know about CHP. I know there's some people who are new to FM and so they're hungry to find out more about technical areas, particularly CHP. Everybody's looking for efficiencies, savings, certainly new technology and innovation. So hopefully there'll be something for everybody tonight, both in the presentations and in the networking afterwards. So it provides a great opportunity to understand a bit about the systems, CHP, combined heat and power, and obviously for those that have walked around, an opportunity, if you haven't seen one, to see a system in action. Just a little bit about our group, and I know Phil's just as active. We've got an event, follow-up event on the 2nd of November. Just Google CIBSE FM or go on Eventbrite at CIBSE FM to register. It's about the effects of power over Ethernet. And then also there's a follow-up one on the 8th of November. We do an annual event around about compliance and some of the legal issues around, certainly the new sanction processes around FM buildings and some of the issues that people are really taking seriously around accidents, health and safety and building services compliance. So I hope you have a great evening. I will hand you over now to John to do the first session. Thank you very much.
Hello everybody. Can you see that okay? You can hear me okay down the back? Yeah. So I'm John Hyde. I'm the National Consultant Specification Manager for Ener-G Combined Power. And all I'm here to do tonight is make sure you have a good time. So hopefully you enjoy the refreshments and hopefully you stick around. Ask loads of questions. We're here to talk, we're here to, I suppose, share information on CHP. Okay? So my role really is to do presentations like this, meet consultants, help on specification and early days feasibility. I can see a few people in the room I know, and hopefully by the end of the night I'll get to know more. Okay? So I'm just going to tell you a little bit about Ener-G to kick it off. Our Manchester operation, we've been there about 30, 40 years. Okay? We were owned by one guy for 35 years, up to about 6 months ago, and now we're owned by Centrica. Okay? So you probably know Centrica, British Gas. And seeing as that we use a lot of natural gas in our CHPs, that's probably a good thing going forward. Okay, we operate all over the world. We've opened up new offices in New York and New Jersey, new factory over there. We go as far as Australia and Japan as well. All of that from Manchester. So it's a bit of a good news story for Britain exporting them. Okay. So these are some of our customers. We go across all different industries and sectors. So you can see some hotel and leisure people here, but also people like the NHS. Anywhere we're using a lot of energy, electricity and heat, as long as possible, is where CHP wants to figure out. So I'm going to tell you a little bit more about that, and these are more of our hotel partners that we have. Is there any other people here that are involved in the hotel industry or leisure industry here tonight? Show of hands, anybody in hotels? Very shy bunch, aren't you? You missed the time of day. Anybody involved in development of residential buildings? Okay. So that's a bit more challenging for CHP, and I'll leave Phil answer all those questions. I also work with Phil on the CHP committee in CIBSE. So we'll talk a little bit about that later. But what I spend my time doing at the start of projects is trying to get CHP right. And really, from early days specification, that's where sometimes the problems happen with CHP. Planning applications, oversizing CHP. And they're very hard to fix later on. Okay, so we all know that we were looking at the thermal and electrical sizing of a CHP, and probably it's because of carbon. We're trying to pick carbon targets. But perhaps that's not the best thing to do. But maybe when you don't have mechanical electrical design done, it's a bit of a catch-21. Okay, so that's what I help out on. And we're trying to design for the future here. We're not really looking at the past. We need to think about any future technologies and anything, like Geoff was saying there, that could come into a building that would improve the energy efficiency. After that, purchasing. Something that there's a lot of focus on because we're spending money here now. But people don't realise that you've kind of got two options here. You can come to somebody like us. We will finance and look after the whole CHP. You won't have to worry about anything. Whereas quite often we see a lot more design and build projects happening where a contractor doesn't really think about the lifetime of the CHP. Okay? So CHP, you know, maybe it's like a puppy. It's not just there for Christmas, it's there for life. We have to think of it that way. And I think people in the FM industry, like some of you here, would really understand that. Installation then can be solved. Yeah? If it's a bad specification, purchased in the wrong way, you may have problems with installation as well. There's a lot of things to consider with CHP, vibration, noise, emissions, things like that, location, planning, so we help with all that too. The part I'm not going to speak about is O&M. My colleague Tim and Heather will speak about that later and show you how we look after O&M and keep it going all year long, because that's what we want from CHPs. We want them to run more often and return on your investment is what you're looking for. Okay? And in the end, what we're looking for here, I tried to put together something clever with an acronym here of CHP, but you can stick with me on this. But if we have clarity from the start, and we have a smooth installation, I was going to reduce, but it would possibly in front of that. But we can reduce CAPEX and the life cycle costs here. And sizing, from the very start, we've got to look at sizing. That's where I see a lot of the problems coming. So that's me, just a quick intro. Come and talk afterwards, have a drink, make friends, okay? So thank you.
Thank you, John. Okay, my name is Phil Jones. I've been trying to fix buildings for the last 30 years of my career, and I'm still fixing buildings. I feel like I'm still struggling up the same hill that I always have been. But one of my passions, one of my technology passions over the years has been CHP. In fact, I can actually remember sitting in a laboratory with British Gas in the 1980s with the first packaged CHP being measured in that laboratory. And that's how long CHP has been in the UK, since the early 80s. But some crucial things happened in the 90s that I'll cover later, did actually take a step change and bring this sort of technology into being in hotels like this. So I'm a private freelance consultant. I do feasibility studies, but my sort of voluntary piece is like Geoff. I run a special interest group within CIBSE. It is the Combined Heat, Power and District Heating Group, and we've got 17,000 members worldwide. And it is a network of nerdy people like me who always want to talk about CHP and nothing else. And I'm taking pills for it. Honest. But look, I encourage you to join us. Go on our web. We've got a website, on the CIBSE website. We've got a sub-website. We've got information about CHP and district heating there. We also run a LinkedIn discussion forum where you can post questions like, what is CHP? Or how much is it? Or all that sort of stuff. And people like John and I will answer those wonderful questions. And we're out there on Twitter when we get around to it as well. So enough of that. So I want to talk about what is CHP and the benefits of CHP. So those that know what CHP is, yeah, just bear with me, but you might pick up one or two bits. So this is CHP. Look, I'm going to show you lots of pictures of CHP. You've all got one. Where is it? Huh? It's in the car. Absolutely right. The car is essentially a mobile combined heat power unit. So, you run an engine on petrol, it develops heat, the heat is used to heat you in the cabin or whatever you call it of the car, right? But it also drives a generator, and that generator generates electricity for windscreen wipers and all the other electrical gadgetry that we've got, including your CD. So that is the key principle. It's an engine driving a generator and developing both heat and power. That's exactly what this does in a bigger way, but also, I would say, in a more robust way than a car engine. Because these things have to run a long time. And they have to run a long time so that you get a good return on investment, which is not what you're looking for from a car. You just want to get from A to B and play the stereo. It's sometimes called cogeneration, hence heat and power. The Americans very often call it cogeneration, but we've come to know it as CHP. This is what I would call package CHP. It sort of comes on a skid-mounted box arrangement. You wheel it in, you connect it up, and off you go. Packaged in that sort of sense. Now, the more interesting bit for me is like what's inside the box, and we couldn't unfortunately take the side off the unit that we've seen downstairs, but what we've got in it is much more interesting if I find the right button. So, engine driving a generator, and dotted around the place are lots of heat exchangers that suck the heat out and put it into the building. That's fundamentally what it is. But in being an engine, it's noisy, so we put it in an acoustic surround, and it vibrates, so you can actually put it on acoustic anti-vibration mountings and so on and so forth. I've actually seen these units on the roof of a hotel, over and above, with a bedroom just below it. You can achieve that sort of sound and vibration mitigation if you need to. So, come as a package unit. They come like this, sort of up to about megawatt, 1,000 kilowatts. Beyond that, you're talking slightly more bespoke stuff in a big container. I'll show you a picture in a moment. So, what is CHP? You put natural gas in. It's not fueled on petrol, it is fueled by natural gas. It's a gas engine, and it's got electricity out and heat out. Some people like to think of the heat as a byproduct of the electricity generation approach. But actually, you can turn that on its head and say, well, actually, it's a boiler that supplies a bit of electricity as well. And in a way, that's often the way we're running it in buildings, is as a lead boiler before the normal gas boilers kick in, and we're getting some money from the electricity over here. And so you can see down here, fuel in, electricity out, heat out, and you get a little bit of waste up the chimney, but we're talking about 80, 85, sometimes even 90% efficient. Compared to a conventional approach, it's much more efficient. Conventional approach is essentially power station, 100% fuel in, and 60% of it, you can argue the case, maybe 50% is thrown away as heat. You know those big peppery pot looking things? They are not chimneys, they are heat rejection, they are cooling towers, just simply throwing the heat away. It's mad. And because we build our power stations so far from the built environment, we can't use that heat. And so we've now started to look at utilising combined heat and power much more locally, either in single buildings or larger combined heat and power on district heating schemes. But it's still local compared to Drax or Sizewell or whatever. And so you're actually talking 80 to 90% efficiency here. Over here, you're actually talking 50, if you're lucky, up to 60% efficiency over the whole piece. And that's why we do, that's one of the reasons why we actually do CHP. So key facts, yes, it's on-site electricity generation with heat recovery, typically 80% and greater. often in the, towards 90%. Now, the best sites have a year-round demand for heat. I would not recommend putting CHP in a school, because the hours run in a school and the heat load in a school is small. But somewhere like this is absolutely ideal, because it's got a good base load of heat. And the idea here is you need enough heat to keep the engine running as much as you can. If you can run it 8, 7, 60 hours a year, you'll get a fantastic return on investment. But typically, if you can get in the 5,000 hours per year area, then you're into an economic CHP situation. If you tried to put it in a school, it would probably run 1,000 hours. It would work, but it wouldn't give you the return on investment. And that's why, and I would say this, wouldn't I? I'm an independent consultant that does feasibility study work. You need an independent feasibility study. It's not like sizing boilers. You have to optimise the sizing. We'll come back to that in a moment. But through good sizing, against a good base load of heat and power, you can actually achieve a long-running CHP and a good return on investment. Hotels are absolutely ideal because they've got a high hot water load, not only in the bedroom, showering, bath, that sort of thing, but they often have a pool, a gym with showers, and a big restaurant, or 2 or 3. And all of that collected together gives you a good year-round heat load from the hot water. The hot water, indeed, is probably more important than the space heating load, typically because it's year-round. So, in a CHP, as I was saying before, you've actually got an engine. Oh, hang on, sorry. An engine which is fired on gas coming in here. It's driving a generator. The electricity gets fed into the building. If you are spilling electricity back onto the grid, you probably won't get that much money for it. And generally, a hotel like this will absorb all the electricity that unit downstairs can absorb. And that's where the savings are. But just to pick out a couple of other areas, there are heat exchangers around the engine jacket and in the oil cooler, and also in the exhaust, and that is sucking heat out, putting that heat into the heat, space heating and hot water system. So that's fundamentally what is in one of these. Apologies, this is an old fuzzy slide, but it's one of the best slides I've come across that actually you can point, you can point to the generator and the engine block, and you can start to see 1, 2, and probably 3 up here, I think, heat exchangers. It's very apparent. And they get much more interesting when you take the side off and have a look what's in there. Now, you can do this at a large scale. This is perhaps 1.5 megawatts, or 1,500 kilowatts, that sort of size. And you can see it's more in a containerized box that you can get in and maintain it inside the box. And typically you might get these either internally, but more commonly the bigger ones are situated in a container outside, externally, or perhaps on a roof or something of that nature. But in hotels, you're really looking at what I would call small-scale package CHP. So these are a couple of examples around the couple of 100 kilowatts mark. And down at this level, you might get a couple of 100 kilowatts of electricity, but about 300 kilowatts of heat. So you get more heat than power. But the bigger ones, it's about equal. The heat-to-power ratio is about equal. And so on these smaller machines, typically, find my button, you've got 100% coming in, and you've got 50% heat coming out and 30% as electricity, with a few losses still up the flue. And that's your 80% efficient. It can be a bit more than that. Now, how do you size these? Well, it's quite intricate. You need to really run a half-hour model of the energy loads properly and put various CHP sizes against those heat and power demands and work out the techno-economic outcome of that. And that's what I do day to day. So the energy demand profiles are absolutely critical. And I repeat, a good base load of heat, and that's going to make it run more than the 4,000 hour mark, and then you're going to get into economics. So there's that balance between how big a CHP do I put in and how big is the demand. But the other balance is a very economic one, and that is called the spark spread. And so the bigger the spark spread, the more money you're going to make. What's the spark spread? It is the difference between electricity price and gas price. And the wider that is, the more money you make. And I'll show you some numbers on that. But if you've got a position where your electricity is 6p and your gas is 4, not that we're in that situation, then CHP doesn't look good. But currently we're talking about 10p per kilowatt hour for electricity at least, and 2.5 for gas. So the gas you're putting in the machine is relatively cheap. The electricity is where you make a lot of the money. And sorry, just to go back, you can actually see onboard controls, monitoring. These are very sophisticated machines. Anybody who had a look, there's a live display of what that machine is doing downstairs, out there. These are very sophisticated bits of kit that are being monitored in great detail. Now, let's go back to that sizing. You take a very conservative approach. So here's my thermal load, and I've got the CHP here just doing the base load. And that's often the myth goes around that you just size CHP on the base load. I think that's far too conservative. You're not getting as much out of it as you would if you went for a slightly bigger CHP here, but in summer, what the load is lower, but what we're doing here is modulating the machine. And this is a thermally led or heat-led strategy in sizing. You're following the heat load. And excuse me, I had flu over the weekend, keep away. So the other approach to sizing is more of an electrically led. So you're following the electrical load to generate as much electricity as you possibly can, and then in summer you will possibly end up with some excess heat, and you get rid of that by a heat rejection radiator. And this system downstairs has 2 heat rejection radiators to do just that, to allow you to follow the electrical load. And those two, that heat-led and that electricity-led approach will give you different economics and different answers. But in general, in a building like this, all the electricity will be absorbed in the hotel, and therefore you are displacing all of that orangey bit as 10p a kilowatt hour that you would have had to buy from the grid. And that's where you really make big money on CHP. Let's just have a look at that. Typical balance for a machine that, like the one downstairs. So we've got a 230 kilowatt electrical, E meaning electrical, so it's giving 230 of electrical out here. This gives 357 of heat, and you're putting 716 of gas in. So, how much is that costing us to run? Let's take it over one single hour at full load. It's costing us in fuel £17.90 to run it for 1 hour. Doesn't sound an awful lot. And you can see the gas price, it's 2.5p a kilowatt hour there. And on top of that, we've got to put into the feasibility study numbers the cost of maintaining that engine. These things don't run without good maintenance, and that is fundamental to how they actually achieve the savings. But you've got to pay for that maintenance, just like you have to pay to maintain your car every year. And that is quite a high number, I think John would tell you, but actually it's a premier of O&M package. So it's costing us £20.90 to run it. how about what we're getting revenue from? We're actually offsetting 230 kilowatts of electricity at 10 pence and 357 kilowatts of heat divided by a boiler if you had to have a boiler. And so the hourly energy saving is £34 and 9 pence. So let's just draw this back on. There are the costs, right? £20.90. There are the savings. And the real way to look at CHP is the net hourly benefit, right? So for running 1 hour at full load, that 230 kilowatt machine downstairs is earning 13 quid. Now, 13 quid doesn't sound a lot, but that's only 1 hour. If we can make it run 7,884 hours a year, then we'll be making £100,000 profit every year for 15 years or whatever the life is. And that's under a 3-year payback. It's a fantastic energy saving and cost saving and carbon saving approach. Now, I just want to finish by mentioning 2 aspects that I feel are really key to all of this. When I started playing about with CHP in the 1980s, we had something called the Fiat Totem. It was a Fiat car engine, literally a Fiat car engine, and it was being maintained by the hotel. So they would sell the box and let the hotel deal with it. And they forgot to top it up and put water in it and oil in it, and they fell over left, right and centre. CHP started to get a bad name. But through good maintenance that we've been doing now for 20 years, that maintenance is what gives us good reliability and availability. And part of that maintenance package is exactly what we've just seen out in the drinks lobby there, which is detailed monitoring on an hourly basis, on a 5-minute basis sometimes, of real hard data. And John spends most of his time sat there looking at a screen and saying, oh my goodness, the piston pressure is too high, the big end's going to go next week. And so he puts a big end bearing in his pocket, he gets in his van and he goes down to fix it before it makes a mess of itself. And so actually that planned, condition-based maintenance is what really makes these things run and run well. And generally, all of that package of monitoring and condition-based maintenance and the maintenance itself will be done these days by the suppliers under a maintenance contract. You try doing the maintenance yourself and you will probably make a muck-up of it. And that, to me, is what happened in the 90s, that we started to do this condition-based maintenance and much better maintenance, and as a result, very high reliability and availability from these machines. So there's a lot of cost savings in CHP, and you saw the payback I quoted there. If you keep it going for 7,000 to 8,000 hours a year, you can produce less CO2 emissions. It can even provide an element of standby because it's there running all the time. A lot of standby generators won't even run up when you try them. And it's absolutely ideal in hotels, but also hospitals, anywhere where there's accommodation, high hot water loads, or things like swimming pools. So I'd encourage you to actually look at CHP in more detail in those sorts of buildings. Thank you very much for your time in listening.
Energy Combined Power.
And I'm Tim Shepherd. I'm one of the key account managers, and one of my key accounts are hotel industry, leisure industry, as well as many others.
I was just going to give you a quick introduction to the operations team, and then Tim's going to tell you a little bit about the monitoring. So we have 700 units that are operational up and down the country, ranging from 4 kilowatt in a little Tesco Express up to 2 megawatts on pharmaceutical sites. So as both of the guys have mentioned, we've got hotels, leisure centres, hospitals. Martin and I have been to another hotel this morning. We've got units at Chelsea and Westminster Hospital, not too far away, so we have a variety of different applications. We've got approximately 50 service engineers up and down the country, so furthest north is a guy in Aberdeen, and then we've got people down in Brighton, Portsmouth looking after CHPs on the south coast and right onto the Isle of Wight as well. So we cover the whole of the UK, 700 units, and as both the guys mentioned, one of the important things for monitoring the units is the monitoring systems themselves. So in order for us to know when the unit needs servicing, if there's a problem, if there's a low water level, high oil temperature, things like that, we have our monitoring system. So because we've been in existence for over 30 years, we've got quite a few different types of monitoring systems. A little bit like if you think of your phone, you used to have a Nokia with Snake on, and now you've got an iPhone which runs on an Apple. So that's really how our control systems have gone as well. So Tim's going to tell you a bit about that.
Yes, thank you. Right, I've got to work this thing as well. Is that the laser? Yeah. Okay. So, some of you may have already seen the system downstairs, had a walk around down there, and then in the bar area we've got the monitor set up, and that's displaying real-time data from the machine down in the basement. That system is called G-Control, but the first system that we designed was around 35 years ago. It was in conjunction with Manchester University, so it's a university project, and it's the DERMS system at the top there. This was our first generation control system, and it formed a fundamental part of the CHP design and the CHP package. It enabled us to install the CHP units into locations like you've seen today, but still have visibility from a remote access point of view. The DERM system was really DOS-based. It was quite a simple system with a binary code type of setup behind it, and it used zeros and ones to identify the position or a failure in a circuit. We then moved on to G-Control, and this was acquired through an acquisition of a company called Nadalo BV in Holland, and we inherited, it was then called RMS, around about 2005. We developed it and worked on it for a period of 12 to 18 months, and then we rebadged it as G-Control, and at the moment this is our sort of most popular control system. Again, very similar to DERMS, but this gave us a little bit more, a few more viewing screens, and as you can see out in the bar area, it gives us a lot more access to data, constants, sort of nuts and bolts behind the system. And both these systems are connectable via a modem. So we have a modem inbuilt into the control system in CHP, and then we have a modem system back in Manchester, and it transfers data through B2 phone line. Then, approximately about 18 months ago, the design team at Ener-G began to developed and tested what we now call the Ener-G e-power system. Primarily, it's designed to go onto the internet, and as Heather said earlier, with applications and with everyone being more app hungry, I think the design ethos was to try and make it user friendly, access through a single web page, have icons and display screens that were simple to use, but the system can be used by an energy manager looking at data, or an engineer trying to do remote diagnostics on the system. So it covers all the bases in terms of information we need, and it can be drilled down into a bit deeper. So what ePower does for us is we can check the fluid levels, pressures and temperatures. It allows us to store data, playback and logging. So if we have a particular fault, we can actually play screens back and then review what occurred and what was the possible cause of the fault. We're monitoring approximately 250 plus parameters. We can see live electrical outputs. We can adjust parameters remotely. This could be reducing the output electrically, or we can change set points to enhance performance. The system has alarm and SOS in alerts, which can be done through SMS or emails. So effectively, if the machine has a problem, it can send out an automatic email to the required person, whether that be the end user, the engineer, the control desk in Manchester. It also provides us with analytical tools, and you don't have problems with that way, remote access and diagnostics, and then we've got metering information, and then finally, with the metering information, we have planned maintenance. We base all our planned maintenance on hours run. So typically the service interval would be at 1600 hours, and the metering on board will count that down to us, and it will give us a warning prior to the servicing needs to take place. We can also use it for things like overhauls, so we can plan the overhauls for the top end and the major overhauls. Because it's an engine, it will need new cylinder heads, pistons and internal components, and we can put all that into the database as well, and it can provide us with warnings for that. This was going back really to the ethos of having a app-based system with simple push-button icons, easy to read displays, so that all levels of users can understand and view it. And it also then, we can take display events to enable remote diagnostics, ability to remote diagnose, reset and restart the unit. So as some of you joked about in the bar area, we can, up here, we have the ability, or the high-end users have the ability to reset and restart the unit remotely. We can adjust the parameters and time clock, and obviously it gives us the real-time metering, access to metering data. So the energy managers can click onto their part of the screen, and they can take the live meter readings, and they can look at how the unit is performing in terms of gas used, electrical output, etc. Now, this is going to be the fun bit. What we wanted to do was try and do a live demonstration, and they say you should never work with children, animals, and live control systems. So, because ePower is not fitted downstairs, we've chosen one of the leisure sites, which is David Lloyd Brighton. It's been in operation 2 or 3 months now, and as you can see by the little live flashing button up the top there, there we go, that the machine is live. Right, you okay?
Yeah. Oh, we just put the meters on.
If you put, oh yeah, put the meters on. If you put the, if you can, the heat projection, that next one. PID, that one. No. That one. John's having this one. Okay, right, there we go. So if we start at the top, this part is showing us that we've got a live connection, and when we talked a little while ago about live playback, we have. Okay, well John's got that. While we've got live playback, this enables us to do diagnostics. So within ePower, we have guilty, alarm, warning and info. And this is basically a script of what's going on with that machine. Now I was grateful for the service team, if you go back up to the top, John, the fact that up until yesterday the oil tank within the engine was running low, and so we've had warnings, these red day tank oil level low warnings. Guys have been in today, they've topped up the tank and we've cleared that fault off. But the playback system allows us to review that. We identify the machine by unit number and location up here, and it tells us that load control is active. The machine is generating in parallel mode and we are in automatic. If there was a fault, this would change the status, and the fault reset would allow us to remotely restart the unit and put it back on load. The engine is currently, by a little graph here, producing 149 kilowatts, 150 kilowatts, and the engine, it's showing us rotating at 1,500 RPM, or just slightly below. And also the sync breaker, so the unit is generating onto the building. On the next row, and if you just run the mouse across the top of those, this is where the app part comes in. It tells us that this unit is based in the UK. We've already got a Scottish flag available that will be when Nicola Sturgeon gets her way. We'll have a Scottish flag to put in there for the Scottish units. My wife told me not to say that. So there may be a Scottish person.
Maybe you could have just said about our Italian unit.
Okay, so we have Italian units. So we can put that in there. What was that? Sorry, John. What was the?
That's the UCPR.
Yeah. So that's a machine operated by us. The fuel type is natural gas. The product type is an Ener-G E150. It's a Mercedes-Benz engine, and it's on a DT maintenance contract, a discount energy purchase. So basically, we own this machine, maintain it. That one is not in use, as you can see on the screen, and then we then go through the icons which generate the different pages. So on the first icon is the P and ID, so the pipework and instrumentation diagram, and this is that diagram. It shows us the oil tank, the oil level maintainer, the engine, the generator, and the various aspects that make up the CHP unit. It also shows us the exhaust gas heat exchanger and the plate heat exchanger, and then temperatures, flows, pressures around that circuit. If one of them were to go in fault, so for example the oil tank level was low, that would change to a red colour, and you could simply see that we need to fill up the oil. But if, and the engine would continue running at that point, but if we lost water pressure down here, and it went below the parameter that was set, it would then switch the engine off and go into a water pressure fault. On the right hand side, this is an illustration of the heat rejection circuit. Not all the units have heat rejection circuits, but this particular one has, and it shows us the building return temperature, it shows us the position of a 3-port valve, and the heat in and out of the plate heat exchanger. And typically we would see somewhere around 75 to 80 degrees there, and around 85 to 90 degrees on the return back into the building. If you hit the next one, John, which, no, one more on. That one, yeah. As with the G control, this is a live picture, a live screenshot of the power being generated. So at the top here, this is where the CHP is connected into the building, and at the bottom is the generator. And in between, it gives us various different readings, including frequencies, voltages, currents, and kilowatts. So we know that it's a 150 kilowatt machine, and on that point there, you can see the 3-phase system with 50 kilowatts per phase, approximately. Okay, next one. This is the exhaust temperature schematic, and this is taking readings from each of the individual cylinders. The Ener-G 150 is an 8-cylinder V8 engine, so it has 8 exhaust outlets, and we have thermocouple probes which are fitted into each of these. This then gives us a temperature, and we can do the diagnostics from a point of view. If we've got a low exhaust temperature, we may have a spark plug failure. If we have a high exhaust temperature, it could be a low cylinder pressure. And there's various options on the bottom which John's been activating, which show averages and minimums, maximums. So it's a good diagnostic tool for the engineers. This is overall power demand, which is in things like oil temperature. So if the engine was cold, for example, we wouldn't want to run the engine at 60 degrees, anything below 60 degrees of oil temperature. So the engine will be modulated down. Next, we've got, for the energy managers and the people that are looking at the meter readings, we have the engine running hours, so we have the cumulative, and then we have the daily. So in its life, it's saying that it's run 2,973 hours, and today it's run 19 hours. It tells us when the next service is due, so in 226 hours, the amount of times the engine started in its life, which is 72 times, synchronised, so on and so forth. Then at the bottom, the important bits, I suppose, electric generated today, and in its lifetime, the heat and the gas consumed. And these are all live readings, you watch them, they tick up. The next one, John. As with all our other control systems, we can adjust parameters remotely, so this is just another screen there. Next one, which is the little clock. Hopefully it'll work. It might take time. Never work with animals and children. On this part, really, it should come up with, because the internet connection's a little bit slow, this will come up with a daily, a weekly time clock, so we can adjust the time clock. So where we have leisure centre users, typically on a Saturday and Sunday, and maybe even on a Friday, they may close early, so we can change the profile for each individual day. So if you just close that one, John, then it'll come up. Just cancel it, that's it. Oop, there we go. That one's on. Yeah. That one. Oh, you can do that one. One of the differences with ePower is that we tried to incorporate all aspects of the CHP package. With G control and with DERMS, it wasn't always possible to get a live view of heat rejection and building site loads. So what this graphic shows really is that we've taken a reading from the main building incomer, and the building as it stands at that moment requires 177 kilowatts of electric. So the generator we know is 150 kilowatt, and they're importing from the grid 28, 29. So it gives us a live view. The rest of it is based really on ensuring that the engine, as Phil touched on, was not exporting to the grid. So we want to use all the generated power on site, and then there's a way that the system can modulate back and follow building load. Okay, next. Whoa, that's it. Yep, cool. So that was the live demonstration of the new control system, ePower. So the final two slides I've got really are, so how does the real-time monitoring work for energy? What do we do with it? We have a central database in Manchester called CPOS, Combined Power Operating System. I may have made that up at some point, but I think it sounds fairly good. And basically the data from all of our CHP units, whatever the control system, gets uploaded into the head office, into the server system. That data is then, so that's done at 2 o'clock in the morning, and that data there is available for us the next day to review, to report, and to trend operating parameters on. With the data being held at Manchester, we then have a control desk, and then we can look at the requirements that are needed. So we can have, if we've got a breakdown, we can task the service engineers, or if we've got the need to plan maintenance in, whether that be overhauls all the information is there and we can act accordingly. And then really it goes full circle. So also the data from the from CPOS, or from the CHP to the CPOS system, then allows us to create our declaration of performance at the end of each month. So that's a reporting method to show the monthly output of the unit. We can also do weekly reports and bespoke reporting for clients. There's one client in particular, he likes a daily reading off of all his machines. So that's what it can give us. And then things like the declaration of performance are then used for CHP QA purposes, so looking at the usages, etc., and for CCL, PP10 type claims. And that, I think they've all touched on it so far. All the systems are still made in our office, in our factory in Manchester, and then the office down there too. And we proudly wear the Made in Britain, Great Britain emblem. So that's really, there we go. Thank you.
I think we've got time for a few questions from anybody from the audience on any of the sessions or discussion.
Oh, is that all right? Sorry.
What was the section?
I'll be very, very quick.
So, okay.
Thank you. Sorry, Geoff.
You have control.
Okay. Won't hold you back much longer with this. I'm Martin Wade, I'm Business Development Manager for Ener-G. I've been involved in CHP not as long as Phil, but just over 16 years. And in the energy business, about 30 years actually, previously, with what was the Electricity Board, regional electricity companies they are now. So what I really want to do is just run through how to minimise CAPEX and risk. Phil has covered some of it, so those slides I will flick through a little bit quicker. As Phil said, there's different ways of sizing a CHP. One is based on a thermal sort of base load, and you size the CHP accordingly. And then the boiler plant will cover any peaks generally during the winter periods. Get the balance. It can be risky, but providing you take an objective look at it and understand what the site's doing and what the requirements are, and also what the spark spread is, what other costs are involved, then that can be another solution. And you can, with CHP QA, you can reject up to around about 30% of heat and still maintain good quality CHP. And I think it's fair to say that if the spark spread is big, then obviously that can be a viable solution. Electricity base load, making best use of electricity. As you can see there, that all of the CHP's electrical output would be used on site, and any top-up would be taken from the grid. Like I mentioned when we were doing some of the tours, all of this is seamless. The site doesn't see any change in the lights or anything like that. It is just like drawing power from the grid. Each sector's got its own scenario, and I know today we've sort of really honed in on hotels and leisure, but there are lots of opportunities out there. And we are doing a number of projects now that are involving district heating, which is becoming more and more to the fore. Obviously used a lot in Europe, and in some of like the Nordic regions, so that's becoming very, very popular. Our base sort of is really hotels, leisure, hospitals, We also get involved in anaerobic digestion, so biogas. Storage is slightly different for biogas, in that the way you size it can be slightly different. There are different incentives, different drivers for it. When the government are changing, of course, but they do seem to be forever changing. So really, if we're looking at CHP sizing, typically, if we go into a brand to look at a new site, current utility profile tends to be electricity, gas and water. We would then look at the implementation of demand side reductions on those three different sources of energies, which will be shown there. We would then start looking at improvements, so any plant efficiency improvements you can do, again across the various utilities, so that could be motors, lighting, pumps, lots of things. And then, as you can see, the utility cost gradually is coming down. And then, when we look at implementing combined heat and power onto the whole solution, then your utility costs will drop even further. You're making efficient use of all the gas, post-solutions electricity, i.e. sun is generated, sun is from the grid, and efficient water usage taken into consideration as well. Just looking at a little bit about comparison between typically hotel and leisure and residential. As you'll see, hotel and leisure hours run generally will be a lot higher in general. The electricity load is constant against residential load, which is up and down. Thermal load is constant. Residential is up and down and can be very dependent on people's lifestyles. Legislation, private wire capability could be used in hotel and leisure. It's something that is being looked at more and more. I'm looking at a project at the moment which involves district heating, private wire capability, and 7.5 megawatts of generation, including feeding back to the grid. With residential, you are tied into regulated electricity market. CHP drivers, slightly different, return on investment, which is something that Phil was speaking about. Whereas on residential, there's the Part L building regs and the carbon tax and various things like that. And quite often, CHP size is maximised for return on investment on hotel and leisure or commercial premises. Residentially, there is a big push for balancing the carbon. So what do we look at as what the stages of our projects? How do they tie in with the various city strategic aims? Well, arrange CAPEX finance to finance a project. That needs to be looked at. Calculate energy cost savings. Calculate the reductions in the carbon footprint. Because gas CHP is still probably the most cost-effective way of reducing the carbon footprint and output. Audit of electrical plant and equipment, tying with the slide a bit earlier about reducing and demand side measures. Audit of the heating system to do the same. Agree contracts, mobilise contractors, project management of the works on site, and then agree FM and operation and maintenance contracts. So you can see it's a process that we would follow through. Just to finish on, up to now we've talked about projects being financed and capital purchase. But one of the very popular things, especially in leisure and hotels, is what we call our discount energy purchase scheme. With this, there is zero capital cost to the client. So the client would get the equipment, as you see downstairs, the CHP, dry air cooler, all the installation work would be paid for by us. We would finance that. It stops any disruption from the core business. When you talk to hotels, you know, they need to make sure that the rooms are right, that the front of house is right, you know, that the cooking facilities are right. They've got lots of other distractions to keep that hotel running because there's a lot of competition there. We can take that away and not draw off from their capital. We will provide energy cost savings. Agreed, not as much as a capital purchase, but we will provide energy cost savings to make that project viable to the client. We will reduce the carbon footprint the same way as we would if it was a capital purchase. Power security, there's an element of power security in that they've got CHP running, and it could be that it could be utilised as a standby engine to support power loss. It also gives enhanced boiler capacity because that will become the lead boiler then, and so you've got more flexibility in your boiler room arrangement and your plant room arrangement. The way we do this is we charge the client a kilowatt hour rate for electricity, and that kilowatt hour rate will always, and in most cases, be substantially less than what they can buy for from the grid. There would normally be a 10-year contract. It includes all the operation and maintenance, all the monitoring, so everything's included that, so it's all encompassed. So it's well worth considering this, as I say, especially for the leisure, for the hotel type industries, because they do like this approach. Okay, thank you very much.
Right, now I think anybody wants to ask any questions. There was one question there someone wanted to ask. You had a question?
For me? Yeah, I did. It was just looking at this great sort of interface that was being shown and all of this information that could be gleaned off it, and the remote monitoring from Manchester and all this.
Yep.
Is there a limit? Do you have a limit for size of operation that you would offer that to? Or would you offer that to anyone with a 4 kilowatt installation? Or?
Yeah, it's open to all. The only restrictions that we have, there may be an element of cost, and then also there is a licence agreement. Obviously, we have to protect our IP.
But you would be able to cater to a small residential site or a large.
That's the whole reason behind the redevelopment of the system and making it more user-friendly to all people. So
some of the older models from about 25 kilowatt down probably would have a slightly different setup, but everything from that size up is normally manufactured with e-power as standard.
You're on about the micro CHPs.
Not necessarily. I was just wondering whether
That's the only, what John's saying, the limitation is the micro.
So 25 up would be okay.
Any other question there?
William Orchard, London Limited. I was wondering if you're doing any work on looking at actively managed packages for the network operators to operate and generate. Because it seems to me if we're going to secure our electricity supply, it's bloody stupid putting them out in a field somewhere connected to the national grid, where if I am ISIL, I would take out the grid supply point. When I was up in Manchester, I was asking how many lines, this is the Energy Networks Association, people thought we need to cut some lights out in Manchester. Well, it varied from 2 lines to 8. And it just seems to me that your industry has a huge opportunity for putting all the generation we need now on the distribution network. But if you do that and it's operated by them, they will need an actively managed generator, which they can manage. So my question is 2 questions. 1, what are the issues for you to make your equipment so that it can be actively managed? Because normally at the moment for an emergency you have to switch it out, take it off from actually operating in parallel with the grid, and then switch
We
But
do,
good question.
yeah, we do have some
All I will
sites.
say is there is a potential market, in my opinion, of 10, well, let's say, there's 10 gigawatts of wind he's backing up. The distribution companies have got a stack of problems as of National Grid on foreign changes. The CCGT is inappropriate for doing it. Look at what Water can do and how fast you're in.
Okay, so let's try and answer the question.
20,000,
Right.
20,000. Thank you, Phil. Thank you very much, Phil. I'm just saying, the market
Yeah.
out there is maybe.
But you put two very good questions. Let's try and answer those. What we're talking about is.
I want Ener-G to answer, Phil. Thank you.
I'm trying to help Reed get to an answer, right? What we're talking about, for those that don't get the question, is actually, in effect, these units locally supporting the national grid by running them that bit longer to actually offset against things
I'm
like.
not, Phil,
Well,
talking about that at all. I'm talking about putting these units in to decarbonise the whole of the domestic sector. I'm talking about putting the equivalent of 10 gigawatts of it in, of 500 kilowatt units,
yeah,
at the local transformers, feeding local houses. All right?
We'd love
That's
to do
what I'm
that.
talking about. All right?
so you've
Nothing
got the
to do
answer.
with National Grid. National Grid, as far as I'm concerned, are dead. It goes to the distribution companies that are 30 times the size.
But to be fair, you talked about others operating their or triggering their units.
Working with them.
Well, we'd
Well,
love
that's
to
what-
be
that's what I was
introduced to
just
those
talking about.
parties. So I think you've a very good point there, that we do have an opportunity in this day and age. All markets are being disrupted at the moment. So energy is the next one. We're in the right place to do that, and maybe in the next 5 to 10 years we will do that. Technically, we can do that.
Yeah,
And
we
we're
do.
already doing that.
Yeah, we do have schemes that run on uninterruptible, so that if the power goes down, we don't have to switch them off and back on again. So to sort of answer your first point, I think. And then your second point about us generating electricity onto the grid. Again, we are working with people on bigger schemes. Probably we wouldn't want to name those at the moment, but on big schemes where we are generating electricity and putting that onto the grid for things like when the wind turbines can't run because it's not windy enough, but it's a dark winter's evening and everybody's watching X Factor, so there's no solar, but there's no wind, and CHP can run then. So yeah, we can look
Take
into
batteries as well.
Yes.
Be part of the puzzle.
The other thing that would factor in and help all of that is more thermal storage.
Yes. Yeah.
And on the bigger units, like the big containerised ones that I showed, we're very often putting in thermal storage so that you can actually make those units run longer, get more electricity back onto the grid to support the grid in the way that we were alluding to.
Okay, another point. No question here. Anybody else with a smaller question?
There's one towards the back there, please, yeah.
Robert Prudence from Silva. As I understand, there will be like 3 options where you sell your equipment. One option is when you have a contract with, let's say, a hotel, install the equipment there, and you fully run it. You take responsibility for it, and all you do is just sell electricity to a customer.
Free heat. They heat the supply free.
And that's one option. Second option is when you do similar things. So you actually sell the equipment. You take up the maintenance contract. Yeah, so the client pays for the equipment, takes the benefit of having a cheap electricity. He pays for gas, but you do the maintenance, and the client pays for the maintenance. Yes, and the third part of contract is when the client buys everything and has independent maintenance company. Yes, how the sharing of the data that you collect about the operation of the equipment, how it is organized in terms of who owns the data, what the third party monitoring equipment, how it can connect to your equipment, and how the database in Manchester can be accessed by third party companies. How do you see that?
We would usually give that access to the end user rather than to the contract. So if you had a CHP in your hotel, we would look to give you the access and sign up to a software license, so you could access what Tim showed you there, and then you could then say to your third party, the oil needs topping up, or spark plugs need changing and things like that. So that's how we typically work.
So if there is a maintenance company and they want to change how the system operates, can they integrate these let's say sensors and the output of your system into their system?
They could
Or
use a
they have to
Modbus.
use
They
your
could use
software and do it through your software.
They could have a Modbus connection if you wanted to do something like that, or take bulk-free contracts from the unit. Do something like that.
I think, it's possible.
So they can access it through a model system separately.
So that the control system has the facility to bolt on extra hardware components. And that can actually work the other way as well. That can give you more visibility, because those input outputs can be taken directly onto a BMS system. So in effect, you could have a system that you just view the CHP from a BMS system.
But the latest version, you were saying, is cloud-based anyway.
Yeah, cloud-based.
So just go on the web and see it.
Yeah.
As long as you've got a password to access it.
Yeah.
So you see the issue of integration, and if the CHP locally here sends data every set of data every 12 hours to the database, so then you cannot actually activate on the cloud until it's uploaded. So it's not.
The cloud.
Power is live, isn't it?
Cloud is live.
Cloud is live.
Obviously, second by second, it's the collection of data, so the metering part
It's not dead, it's one. It's live.
So there's two systems. One is an upload in the evening of everything, and the other one is a live.
But aren't you going to need a hardware and instrument system to really manage the load you're talking about, DCs, etc.? As they do at National Grid, because you can't store electricity. Someone's got to be able to change what's going on your engine very quickly.
You can do that through the e-power system.
Yeah.
That's what we use, the e-power system. Yeah. So we could go on now to the David Lloyd Brighton and change the output of that unit, and it would change instantly. Yeah.
I'm talking about something different. I'm talking about your engine being part of the management of the overall electricity network and being dispatched, if you like, to meet the changes in load. So when the sun comes up locally, your engine goes off.
Yes. So you would just all it needs is a signal to say the sun's come up, go off.
We're currently doing that for our Scandinavia on the store. Project.
Okay, one last question before we break up. I was just going to say, if anyone else has got a question, on the larger system, all the district stuff, it's really good on the machines, obviously the maintenance, the proactive, condition-based stuff. But very much often people then sort of say about heat exchanges, return temperatures, other loads not quite well. Can you share some experience about that? When we start talking about maintenance, and is the design really right, and we're struggling with the temperatures and it's not as it's... Any solutions for that?
Well, I mean, you're swapping over onto district heating. Actually, if you follow the code of practice that was mentioned a couple of times, then actually you can do very successful district heating schemes. The problem is that up until a year ago, we didn't have a code of practice. There were no minimum standards, and actually a lot of district heating, the smaller district heating, has not been designed very well. And we've learned a lot from that, but people are now saying, what do I do with my 50 dwelling district heating that's got a high return temperature and stuff? Well, I'm spending some of my time troubleshooting that stuff because it was poorly designed in the first place. Follow the code of practice is the answer, and you'll get it right.
And to support that really as well with the electrical demand, the actual electrical output ends up being fed into landlord supplies, which are very low in current and demand. So when you're looking at the design, you need to consider the whole picture and size the unit correctly. And if you are able to get the export onto the grid at a value or a rate that's of returnable value, then that's another option that's part of the design.
Generally, district heating, you need to do it at scale, at size, but also you need to do it to supply a number of different types of buildings. I'm still slightly concerned about even larger schemes that are just supplying residences. And what you've got is a peak in the morning and a peak in the evening, and actually that's not that good for district heating and CHP unless you've got massive thermal storage in. What you need to do is get a school on there, an office on there, a hotel on there, and actually get that big base load of heat, and then CHPs will run well, or even heat pumps will run well on a district heating scheme. Follow the code of practices is the way to go on district heating.
Okay, on that then we'll just round up. As Phil mentioned with his CIBSE CHP group and our facilities management group, there's some leaflets around. You can log on online, join the group, be on the mailing list, there's some flyers around. Be more active. I hope you found it informative tonight. We can't leave without fantastic speeches from all our team here, but especially from Ener-G for actually supporting the night, putting it on, providing the refreshments. I understand there's still some more as well to carry on networking.
Yeah.
Those other awkward questions, and thanks to everybody for attending. Thank you very much.
And so, particular thanks to John, who's put all of this event together.